and good morning. It's 4th of November 2020. We are on lecture number 4, I think. And last week we cover on the Fourier series and Fourier a bit of Fourier transform. And today I'm going to continue with Fourier transform. Almost probably I will start from the beginning of Fourier transform, and after that, and before that, I'm going to show you the solution for tutorial that we missed, that we did last week. Okay. Okay. Let me put up the tutorial first. I'm going to share the screen.
Syarifudin.
Okay. You see the slide?
Yes, sir.
Okay. We have go through this part. Okay. Number 2 also we have go through. Number 3 also we have gone through. Okay. Number 4, which is a convolution of u of t, ut minus t1, and h of t equal to ut minus t2. Right? So basically that you have this one function and this another function. Okay, and we assume that t2 is greater than t1 and is positive. Right? This is an assumption that you can make. You can also make assumption of t1 is greater than t2. It doesn't matter. But on this question, for this solution, I make an assumption of t2 is greater than t1 and greater than 0. And you need to plot the y of t. So x of t, which is u of t minus ut minus t1, is actually this function. This what we call it, rectangular function. Okay, because u of t is basically this. This is u of t. This is u of t. Then minus ut minus 1 is basically this function. Okay, so when you add, you get this. You get this function. Okay, so you have a rectangular function. For h of t, u of t, actually this function, this is u of t. Okay, and minus ut minus t2 is this function. So when you add these two, so you get here. So now, basically that you want to convolve between these two functions. So if you look at this, the convolution basically involve at this region, which is less than 0, this region, and also this region. Okay. So for let's say I call this region number 1, this is region number 2, this is region number 3. Okay. Okay. For region number 1, which is t less than 0, so both signals do not overlap. When there is no overlapping, therefore y of t is equal to 0. So basically for this region, for a condition like this is at region 1, where you have a x of t and you have a moving window of h of t. And for t less than 0, so basically it's moving from here, move up to here. Okay, so it does not overlap. So y of t is 0. Right? Okay, clear this part. Then we go into region number 2. Region number 2, when you have we start to overlap. Region number 2 is basically from here to T1. This. So it start to do the overlapping. So H of T start to overlap because it start moving from here to there. So both signal overlap from the beginning of x of tau, where tau is equal to 0, because this axis is tau axis, to the end of h of t minus tau at tau equal to t. So basically that this is the area of the overlapping. So you do the integration of y of t equal to from 0 to t of 1 d tau. So this integration is equal to t. Okay. How do you get t? This one is from your integration. Basically, the integration of 1 d tau is equal to tau. Equal to tau from tau from 0 to t. So therefore is t minus 0. So equal to t. Okay? That's how you get it. And this is the curve. This is the t curve. Right? This is y of t. So t equal to 0, y is equal to 0. T equal to 1, y equal to 1. T equal t1. So therefore y equal to t1. So it will overlap up to here, right? When you do the integration. So this is the y of t. So region number 2. Region number 3. Region number 3, when this type happen. So for t in between t1 and t2, right? So basically that in between from this to this. So this is region number 2. So what happened is that it's always 1. It's always full, right? So it's constant. So from 0 to t1, t is equal to t1. So it's always t1, right? Clear?
Clear, sir.
Yes, sir.
Okay. So from t1 to t2, the straight line. So now region number 4. Region number 4, for t is actually from t2 until t1 plus t2. So both signals overlap from the beginning h of t minus tau and to the end of x of t for t1. So basically that's this part. So the integration is really from t minus t2 to t1 of 1. So you get this t1 plus t2 minus t. So this is the curve. And region number 5, when there is no overlapping, which is for t is greater than t1 plus t2. So there is no overlapping. So therefore, y of t is equal to 0. So you get this. So this is your final curve for the convolution of the ut minus t1. This is x of t convolved with h of t equal to ut minus t minus t2. So this is the result. of the convolution. Okay. So for the convolution, you need to recognize piece by piece where you want to convolve. Okay. So in this case, you have 5 regions. Right? So if you look at basically that y of t is actually equal to the convolution of from what do you call it, minus this one, region 1, for t greater than less than 0. And it's basically minus infinity to 0. It's actually 0 because there is no overlapping. Second one, this is the second region from 0 to T1. From 0 to T1 of 1 dt plus from T1 to 1 dt plus the integration of this region 1, region 2, region 3, region 4. Okay? T minus T2 to, okay? T minus T2 to T. 1 dt plus region 5, which is from T1 plus T2 infinity of 0 dt. So this is 0, this is 0, so you get only these 3 terms. So this is the first one, this is the second one, this is the third one. Okay, so this part is this part is that, this part is this one. Okay, so this is actually the whole equation for the convolution for this example. Right? So you need to recognize the piecewise, the region, the different region and different, which then that region basically you have the interval for your integration. So this is for number 4. Number 5, prove that convolution of 2 unit steps function will produce a unit ramp function. So you need to prove that, okay, f of t equal to ut, convolve with ut, you get r of t. You need to prove it. So how are you going to do that? Let f of t is equal to ut of t convolve with ut of t is equal to, this is actually the general equation for convolution, which is from minus infinity u tau times ut minus tau d tau. So what is u tau? U tau is this shape. Okay? It's a step function. This is u tau. And ut minus tau is this. Okay. So the signal ut and ut minus tau are shown as this for t less than 0 and for t 0. Right? Note that for t less than 0, the non-zero portion of u tau and ut minus tau do not overlap. So basically that when you what do you call it, when you draw this, basically that it does not overlap at less than 0. Right? Okay, here. When t is less than 0, it does not overlap. So because ut minus tau is like this here. So this part not overlapping because of 0. The non-zero part is not overlapping. So this part is not overlapping with this. Okay. So there is equal to 0 for all. Therefore, f of t is equal to 0 for t less than 0. However, for t greater than 0, then the non-zero values of ut, u tau and ut minus tau do overlap. So basically that this one, okay, this graph will overlap with this because it now becomes like this. So this is the part that you have the overlapping. This is t. So for t greater than 0, you have the overlapping part. And this will overlap up to infinity. So therefore, you have the equation like this. Ut, u tau times u tau minus tau d tau, integration from 0 to t. Because the overlapping part is actually from 0 to infinity. So from here, this is your integration. Integration from 0 to t of 1 d tau. This is actually equal to t for all t greater than 0. Therefore, we may write f of t is equal to t times u of t for all t. So this is actually equal to r of t, the ramp. R of t actually is t ut. So you have this. So it proves that the convolution of ut convolved with ut is actually equal to r of t. So that's how you prove. Okay. Selesai.
Sama-sama,
selesai
sir.
five.
Boleh.
Ha?
Boleh, sir. InsyaAllah.
Okay. Nanti
Sir,
saya.
slide ni kat mana, sir?
Ha?
Slide yang ni?
Yang ni saya tak masukkan lagi.
Oh,
Saya tunjuk
patut.
dulu. Ini kan solution of the tutorial.
Oh.
So I tunjuk dulu. So that after this I masukkan dalam apa ni, dalam apa ni lah, dalam e-learning and also dalam MS Team lah.
Alright.
Okay. Tapi all this conteng-conteng tak ada lah. This conteng ni will be in the video. Because I don't save the whatever I conteng. So
Alright,
that is the solution for the tutorial. Okay, any question on this?
Sir, cuba
Yes.
sir patah balik satu slide.
Okay.
Kenapa yang ut minus tau tu kan, dia jadi terbalik lah sir? Kenapa dia tak macam biasa punya unit step? Yang ut minus tau tu, dia punya graph tu dia terbalik. Kenapa dia terbalik sir?
Okay. Because dia terbalik, you tengok dia punya ni. It's a tau. So apa, minus ke apa tu?
Oh, okay, faham. Okay.
It's a reversal.
Oh, so
Okay.
dia negatif. Okay. Dia tahu yang negatif.
So you need to see this. So because when you want to do to show for the integration, you change the t into tau. Okay, because you want to integrate with respect to d tau. Okay.
Okay, sir, insyaAllah.
Alright. So that's why it's balik. Because of the time reversal based on the tau reversal.
Okay.
Okay.
Faham, sir, faham.
Okay. So if you don't have any question, then we can continue with the lecture. Okay, this is actually on the for the solution of the tutorial the other day. Okay, and for the tutorial on Fourier series, Fourier transform, that one I will combine into one tutorial. Okay.
Okay, sir.
And also I will combine with part of the convolution. Right now, convolution I only give you two questions for the tutorial. So maybe I add one more. Then we do that most probably next week. Right?
Baik, sir.
Okay. Okay. The second one, I'm going to go to the lecture for the, let's see, okay. We go to Fourier transform dulu, right?
Fuyo.
Okay, I'm going to share the slides on the Fourier transform. Aduh, saya punya Google not responding pula lah. Ada.
Sir,
Ya,
kalau sir buka slide tadi tu Sat boleh tak tekan mark sikit lah?
ya. Saya apa ni? Saya punya apa ni laptop hang ni.
Oh, okey.
Okay. Saya tutup dulu. Ya, kadang-kadang ni lah dia tekan banyak kali lah. Problem lah.
Interrupt sir. Itulah tu.
Okay.
Okay sir.
Apa soalan tadi?
Nak tengok slide tadi kejap sir, nak tekan mark. Tak, dia faham tapi tak 100% lah.
Apa ni yang saya conteng-conteng tadi dah hilang dah bila saya tutup.
Boleh sir, boleh. Boleh sir, boleh.
Nanti depan ni you tengok dalam ni lah, you tengok dalam apa ni? Dalam video nanti.
Oh, okey.
Video nanti saya akan upload dalam YouTube.
YouTube.
Sekarang,
Alright sir.
sekarang ni saya tak ada upload lagi. Semua video saya tak ada upload lagi. Tapi saya akan upload nanti.
Baik
Okay.
sir.
So, kalau you nak tengok yang tadi saya masukkan balik. Apa ni, boleh tunjuk balik the slides. Tak ada masalah.
Oh.
Okay, kejap saya share balik. Okay, nampak?
Nampak,
So,
nampak.
which part?
Depan lagi sir. Sikit lagi.
Yang ini ke?
Alright sir.
Ni. Habis tu.
Okay dah. Settle.
So, yang ni basically ni lah. Ini saya macam tadi. So that's why dia apa ni, reversal. This way. This is actually for this function.
Tapi memang dia kena ambil T lebih besar daripada kosong lah sir.
Dia basically that you have to do integration from minus
0 to infinity. Oh,
from minus infinity.
to infinity.
So that's why this is actually this curve I want to show for t less than 0. So if t less than 0, so basically that there is no overlapping. Yang ini tak overlap dengan yang ini. Okay. So this I want to show this. And this one is for t greater than 0. So for t greater than 0,
Dia akan overlap. Oh.
actually integration from minus infinity to t of 0 d tau plus integration from 0 to t of
1
d
tau.
So this is 0. So
0
this basically
T.
you get t because this is actually tau from 0 to t is equal to t minus 0 equal to t.
Betul sir.
There. So this actually from t to infinity. You get this. Campur dengan lagi.
Unit RAM.
Yes, this is a unit RAM.
Okay sir.
Okay. Second one, go to the lecture of Fourier. Okay. I'm going to share the slides. Okay. You see the slide? Okay.
No sir.
Now, you see the slide?
sir. Yes.
Okay sir, nampak sir.
Yes. So this is actually the
Bull.
properties of Fourier transform. This is the definition of the Fourier transform. Basically, that x of t is equal to integration from minus infinity to infinity x of f e j 2 pi f t df. This in time domain. This is in frequency domain. So basically, that if you are given x of t, then you can find x of f, right? If you are given x of f, you can find x of t, right? So this is really this part,
Vice versa.
okay? This part is this, this part is this.
Yes.
So basically, given x of t, you can find x of f. Given x of f, you can find x of t.
T.
So the second, this is the definition of Fourier transform. For the first property of Fourier transform basically is the linearity, where if you have ax of t plus by of t, therefore in the frequency domain you have ax of f plus by of f. So with the same proportion, okay, a and b. Time reversal. Time reversal in time domain is also a result in the frequency reversal in frequency domain. And duality, x of t is equal to x minus of f. Time shifting, you shift in time domain, and you have e to the minus j 2 pi f t naught in the frequency domain. This is really the phase shift, right? You know this phase shift, right? Or you don't know?
Sir.
So
Yang angkat graf tu
this time shift in the time domain result in a phase shift in frequency domain. In the when you have a phase shift, a frequency domain, a shift in frequency domain, so you have a shift in time domain. Right? Convolution in time domain will result in a multiplication in frequency domain. So differentiation in time domain result in this time j 2 pi f to the power of n. Right? So these are the properties of frequency Fourier transform. So definition of Fourier transform. Okay. In Fourier series is for periodic signal. Fourier series. Okay. Fourier transform is for a non-periodic signals. But we can also use Fourier transform for periodic signal. Basically that Fourier transform is more general compared to Fourier series. So Fourier transform is another method representing signal and systems in the frequency domain. Okay. So this is a forward form of Fourier transform. X of f is equal to the Fourier transform of x of t, which is defined by integration from minus infinity to infinity x of t e to the minus j 2 pi f t dt. So this is the forward form of Fourier transform. And this is the inverse Fourier transform, where if you are given x of f, then you can find x of t by doing the inverse Fourier transform on the x of f, which is defined as minus infinity to infinity x of f of ej2 pi ft df. Okay, so this is the ift, and this is the ft. This ift. Inverse Fourier transform. This is Fourier transform. Right? Example of Fourier transform pairs. Okay. Find the Fourier transform of this function. X of t is equal to v naught for
negative tau.
period minus tau over 2 up to tau over 2. And the rest is 0. So basically that you have to find the Fourier transform of this rectangular wave. Okay. So this is given. So basically that you have a period of tau here. Okay. So you set up the Fourier transform in this form. This is the
Definition.
Fourier transform formula. Okay. So x of f is equal to minus infinity to infinity x of t e minus j 2 pi ft. So what is f? What is x of t? X of t is actually this curve. And this curve was given by from minus tau over 2 to
Tau over
over 2 is v naught. So this. Okay. So now from here you can see that it's v naught from minus tau over 2 to tau over 2, and the rest are 0. Actually, from minus infinity to t of 0 dt plus t to infinity of 0 dt. So this actually, this part is integration of this part, and this part is the integration of this part. So these are 0. So you only have this. Okay. Okay, which is the integration for this part. Okay.
Okay, so sir.
From here you do the integration, which you get this v naught over minus 2 minus j 2 pi f e minus j 2 pi ft from minus tau over 2 tau over 2. So you substitute minus tau over 2 and tau over 2 into the equation, so you get this v naught over minus 2j 2 pi f times e minus j pi f tau minus e to power of j pi f tau. So this can be written as v naught over j 2 pi f times 2j e to the minus j e to the j pi ft minus e to the power of minus j pi ft divided by 2j. So this is actually the sinc function over pi f. The sine function, the sine function of pi f tau over pi f v naught. So this is equal to v naught tau sine of pi f tau over pi f tau, and this is actually a sinc function. Can be written as that v naught tau sinc of pi f tau. So this is the
sir, kena hafal ya sir? Kena hafal ya yang E, J, pi, F apa semua ni jadi sin tu apa semua?
Yang tu nanti I discuss dengan apa ni, masa Dr. Shida mengajar dulu, dia bagi formula ke tak saya tak pasti dalam untuk exam.
Betul je.
Familiar, at least familiar with the basic function.
Okay.
So basically that the Fourier transform of a rectangular waveform like this becomes this sinc function. This is the sinc function. It's a sinc function. That's a sinc function.
Faham. So maksudnya value dia tu ada kan?
Iyalah.
Value selepas negative t tau minus tu.
Yes. So basically that a rectangular wave in time domain will transform into a sinc function in frequency domain.
Alright.
So there is a transformation. Why do you do this transformation? Actually, in a system, remember a system, let's say you have input and then you have a box, a system, and then this output. Let's say you have S of t and you have h of t,
Okay.
and this is y of t. So y of t is equal to s of t convolved with t,
Y.
right?
H of t.
So to do this operation in time domain convolution is very difficult. So you use Fourier transform, which what does the Fourier transform says? The convolution becomes multiplication. It's actually multiplication of s of j omega t multiplied by h j omega t. Right? So this is actually y,
YT.
something like that. So basically, this is y capital. This one,
Okay.
this yf. So let's say I use f,
Okay.
Basically that it become yf and s of f and h of f. So multiplication is easier to compute compared to the convolution. So that is the purpose that we learn this transform, so that when you have a system like this, you can do the analysis easier in the frequency domain. Okay, so you change the domain to do the analysis better. Okay.
Right. Okay, sir.
Let's say you want to find a Fourier transform for a triangular wave like this. This triangular wave is really given by this formula. X of t equal to V1, 1 minus 2 over tau times the magnitude of t for t in between minus t over tau over 2 and over 2 and elsewhere 0. So this is actually the function, the triangular function, the triangular function. Okay, and we want to find the Fourier. How are we going to set up this? So this is the general formula for the Fourier transform, and this is actually given by this, by discarding this part. Actually, you have lagi plus integration from minus infinity to t of 0 dt plus integration of t to infinity of 0 dt. Okay, so basically this part and
0.
this part. Okay, so this part 0. So this part is actually integration for this.
Oh, one side.
One side. Okay, one side. So basically from this is really minus tau over 2 to 0. So this is the equation that 1 plus 2 over tau t. And this part is actually the integration for this part. Okay? That's why from 0 to tau over 2. So from here to tau. Okay? And this integration is given by this. Okay? Sine pi f tau over 2 over pi f squared. Okay? So this, the integration you need to do on your own. I'm not going to teach you because this is actually calculus. All this. Actually, you get this. You simplify to this already. This. All this actually simplify to this. And simplify further, you get this. And simplify further, you get a sin. So this is actually the representation of the triangular wave in frequency domain. Okay?
Okay, sir.
Fourier transform. So these are the Fourier transform pairs. Most probably that maybe we will give like what. If in time domain e to the minus at ut, then the transform is 1 over at jo2 pi f for all a greater than 0. If a of eatu minus t, then you get this. If it's e minus a magnitude of t, so you get 2a over a square plus square of 2 pi f.
F squared.
So all this. So I'm not going, if a pulse in time domain will give you a 1 in frequency domain. So basically that if in time domain t, basically you have pulse like that. So in frequency domain, you get 1.
Oh.
Okay. So a pulse like this transform to that. So conversely, a pulse like this in frequency domain, in time domain, you get all 1.
1.
And for the cosine, you get this. See, cosine of 2 pi f naught t. Okay. If let's say you have cosine function is something like this, right? Right? So in frequency domain, basically that you have, if you get f here, so basically that you get a pulse here and a pulse here. Basically is, let's say, plus f naught and minus f naught. Okay. So this is time domain and this is the frequency domain. For sine wave, is the, see this imaginary part, j. This is a frequent, what we call it in a real part, cosine and sine and cosine. Okay. So these are some other functions in what we call it for the what we call it Fourier transform, right? So you can go through this. So first properties of a Fourier transform, linearity. Linearity is basically that if you have x of t and transform into a frequency in a Fourier transform frequency domain as x of f, and another function y of t transform into by Fourier transform into y of f. So therefore, the addition of x of t and ax of t plus by of t will give you ax of f plus by of f in the Fourier domain or frequency domain. So this is the linearity properties. The scaling in the frequency domain will result in time domain will result in a scaling in frequency domain. So this is the example for linearity. Let's say you have this function, right? X of t is actually 2 for -2 between -2 to 2, and -1 for between -4 to 2 or to -2, and from 2 to 4, as well as 0. So to demonstrate the linearity properties, we can let x1 of t minus x of t. Okay, so x1 is representing by this. X1 is actually this function. Okay, x2 is this function. Basically, that we decompose the original function into these two functions, and you add together. So you get this, right? So by using the linear properties, and Fourier transform pair for rectangular function, then you can write x of f is
So
actually
add ke subtract so? Dia tambah tolak.
this one actually tolak because it's 3 and 1. So basically this one actually this.
Dia bottom part yang tu lah.
Patut macam tu.
Okay.
So that's why dia tulis tolak. Tolak is basically itulah kalau nak campur dia dia apa ni?
T tu sama dengan 2. XT 2. Okay.
Right?
Alright.
Okay. So basically dia tolak. Saya suka campur because I use this one.
Okay.
I use the function.
Alright sir.
Okay. So this one dia tolak because of dia buat these two function lah. Okay.
Okay sir.
So x1 minus x2. So this one is decomposed to function, and in this case is subtract. Okay. So you get this in the Fourier domain. So this is actually from the what we learned just now. This is actually a sinc function, which is we get this, and this also a sinc function. When you transform, you get this. And you substitute. So basically that you get this whole answer. So this what we call it transformation is using linearity properties, where a single signal like this is transformed, is decomposed into two separate signals, and we use the linearity properties to do the transform. Okay. Time reversal. If given x of t, transform into x of f using a Fourier transform. Therefore, the time reversal in time domain will result in a reversal in the frequency domain. Example, find a Fourier transform of x of t equal to ut minus t over tau over 2. So we get this. This is actually the function. And this is function of x of t. So any function f of t may be represented by the sum of two components such that f of t equal to f even of t plus f odd of t, where f even of t is ft plus f minus t over 2. F odd of t is equal to ft minus f minus. So you decompose f of t basically into even and odd. So you add the even part and the odd part. Right? So basically that the function just now is this. X of t, x of f is actually equal to the integration from 0 tau over 2 of e minus j2 pi ft dt. So it's the integration of this part. Okay, from this, from 0 to
tau over 2.
Tau over 2. Okay, from 0 to tau over 2 of 1 e minus j2 pi ft dt. So this is when you do the integration, you get this. So this is really if you do a direct integration, but if we use this even and odd parts, the x of t basically can be written in x even of t plus x odd of t. So this is the x even of t, basically x of t plus x of minus t over 2 So this actually can be transformed using Fourier transform x even of f into x of f minus x minus f over 2. So if you do that, so you get this. You get sine
Wow.
x sine pi f tau over 2 pi f. Right? This is for the even part. Now if you do for odd part, x t minus x minus t over 2 is transformed into x odd of f, x f minus x minus f over 2. So you plug in that thing, so you get this part. So you see that this part, okay,
Equals
is
to that part. Oh.
equal
So
to
yang ni sir,
huh?
ni sebenarnya calculation dia atas tu je lah. Tapi yang ni
Yes.
dia nak buktikan yang tadi even tambah odd tu
Yes,
jadi.
yes,
Okay.
yes, itu je.
Wow.
Okay. This is time and frequency duality. So, if in time domain is x of t, result to x of f, therefore, in time frequency duality, basically that the x of t result in x is small x minus f. So this is the time frequency duality. Okay, use the duality property to find the transform of y of t sine 2 pi f naught t over pi t. So the solution. Okay, this y of t equal to this. Okay, this actually can be written as this. Okay, you can rewritten this function into this 2 f naught sine 2 pi f naught 2 pi f naught t. Why do we write this? Because this is actually sinc function. Okay, so you can write as 2 f naught sinc 2 pi f naught t. And we refer, if you refer to the table, the pair number 17, if we refer to this table, okay, so this is the basically that tau sinc pi f tau will give you a rectangular of t over tau. Okay. So x of t is equal to rectangle of t over tau, transform into x of f of tau sinc pi tau f. So by applying the duality, okay, by applying the duality, we can get x of capital X of t is equal to tau sinc pi tau t. Therefore, transform into x minus f, which is rectangle wave of minus f over tau. That tau equal to 2 f naught, then you can substitute this, so you get y of f is this.
Pening ya sir.
So this is really the sum of the properties now. Nampak tak? Remember?
Pening.
Hello.
Pening. Yes. Siapa hello tadi? So, nampak tak? Basically that is what it says is that if a sinc function in time domain transform into a rectangular in the frequency domain, so a rectangular in time domain we transform into the sinc domain, sinc function in the frequency domain. Itu. That is time frequency duality. Yang saya tunjuk tadi, ingat tak? A pulse in time domain will give a 1 in frequency domain. Ingat? And a 1 in frequency domain will give you a pulse in frequency domain. That is the duality. Sama je this one. So, mana yang saya draw tadi? Ni. Okay. This. A pulse in frequency in time domain will give a 1 in frequency. A pulse in the frequency domain will give a 1 in. So that is time frequency duality. Right?
Okay, sir. Hello.
Yeah. Dengar tak?
Hello.
Yes.
Okay. Line slow, sir. Sorry.
Okey dah.
Line slow tu.
Duduk B.
Yeah. All of you dekat mana?
Kat rumah tu, rumah.
Rumah.
Line rumah Ihsan slow je.
Oh, okay. So basically that time frequency duality is that you just need faham macam tu je lebih kurang. That is the concept. That if it's a rectangular, transform into a sinc function in the frequency domain. Therefore, a sinc function in time domain will transform into a rectangular in frequency. To time frequency duality. So this example is given a sine function. This sine function is actually a what? Sinc function. This. So sinc function in time domain will give you this sinc function in time domain will give you a rectangular function in frequency domain. So a rectangular in time domain will give you a sinc function in frequency domain. That is the duality. Time shift is you have a shift in the time domain by T naught. In the by Fourier transform, you have a, what is this? This is a phase, right? Phase shift.
Phase. Yeah.
Okay. So given x of t, this function, okay, by shift x of t to the right by pi over 4, shift x over t to the right by pi over 4, and find its Fourier transform. So basically that you shift this function to be this lah. Right? So it becomes like this when you shift. Solution. A rectangular function of this will transform into thing.
Sir, back satu slide, sir.
Okay.
Yeah, okay. Alright. Boleh dah.
Ni lah. Okay.
Okay.
So it shift like that. So basically that this transform, this what we call it, if x of t is equal to rectangular t over tau over 2 transform into x of f tau over 2 sinc pi f tau over 2. So therefore y of t equal to x t minus tau over 4. Basically you shift, then the result is also for transform is that you have a phase shift of that. So you just plug in the what do you call it, this value of t into this. Right? So you get this. So you have this part, which is not there because there is this one is no shift. So with shift you have this additional term. So this is the additional term that you add. Then you put in the you kembangkan and you simplify, you get this. Right? That is the answer. So you have a phase shift. This frequency shift, if x of t transform into x of f, then a shift in frequency to the left, you get this, and shift to the right, get that. See this? Eh?
Okay.
Just apa ni, you tengok the sign ni, then basically you inverse the sign lah in time domain of this term E tu. Eh? So x of t, if you have this x of t, e to the j 2 pi f naught t plus e minus j 2 pi f naught t over 2, then you have this x f minus f naught plus x f plus f naught over 2. Or this is actually similar to x cosine of 2 pi f naught t is these are frequency shift properties. Example, find the frequency transform of x of t of y of t equal to x of t cosine 2 pi fc t, where x of t is equal to 2 f naught sinc 2 pi f naught t. So the solution is that for frequency shift t, this is the property just now from x t cosine 2 pi fct transform into x f minus fc plus x f plus ft. So this can be transformed into this, whereby applying the duality x of t 2 pi naught sinc f2 pi f naught t, you get this rectangular, right?
Aduh.
This basically you have to go to the table of sinc. Basically, sinc in time domain, shift into rectangular. Transform into rectangular in the frequency domain. So whatever terms dalam ni, you kena tengok lah. Balik dalam apa ni, in the table tu, right? I'm not going to go through that. That one you have to, right? To be familiar with the tables. So this is actually, please, this table. Yang nombor 17. Nombor 17. This. Okay. This basically rectangle of t over tau is equal to tau sinc pi f t pi f tau. So you ambil this, transform, because this part is f not tau ni is tau lah, not itu, yang transform tadi, Okay, frequency shift, sambung lagi. From the frequency shift of this, we'll give this. So y of f is equal to the rectangle of half of a rectangle f minus ft over 2 pi of pi naught f naught plus rectangle of f plus fc divided by 2 f naught. So if we draw, so this is the function. So this actually is this one finally transform into cross, right? Okay. Convolution. This is important. A convolution in time domain result in multiplication in the frequency.
Multiplication.
Okay.
Frequency domain.
So basically that if you have system like this in time domain, x of t, y of t, this is n. So this is equal to x of t convolved with y of t. This one, okay, f y result to r of f is equal to x of f multiplied by y of f. This is frequency
Pening.
time domain. Okay, so this is the convolution property. Eh? So let's say you are given two signal. F1 of t is e minus a t ut, and F2 t is equal to e minus b t u t. If f to be an output of a convolution process between the above two signals, find the Fourier transform for f of t. So basically that if f of t is equal to f1 t convolved with f2 of t, so find the Fourier transform. So basically that you need to find of f of f. So f of f is equal to f1 of f multiplied by
F2.
of f. Rasa saya punya grafik tablet ni ada line-line tu. Jadi dia automatik terkeluar line tu bila saya tekan.
Alamak.
Patutnya tak ada ni
Alamak,
line ni.
Mana ni Faiz?
Macam saya tertarik je.
Tak ada pun. Saya tak ada tertarik pun. Saya just tekan dia automatik keluar benda.
Tak tahu saya.
Ini Hayon punya graphic tablet saya pakai. A, find the Fourier transform for f of t, and B, signal f of t by using inverse Fourier transform of A. So basically, the second one basically to do the inverse transform lah. So first part, okay, from Fourier transform pairs, this one you look at from the table. E minus AT UT is transformed into this. So this is actually from the first, I think. Kita tengok
Ayah.
Go back to the tables. This first table. This. So E minus AT UT. So the 1 over A plus J2 F. Okay. So we use the table. Okay, this. We give you that. And F of T of this. Tengok, automatic dia pergi. Bagi. Automatic dia bagi line. Aduh. So, by using convolution, when you convolve two signal, it transform into this. So therefore, you can do the convolution by just multiplying the transform of f1 and transform of
F2.
So you can write like this. So this is actually f1 of f this is
F2.
so you get this is the
Answer. Yeah, simple, sir.
simple if you know this first transform.
Yeah.
If
Kenapa
you
lah,
don't
sir?
know, it's also difficult. Most probably bagi kot, I think lah. Okay, now for
Oh
part
my
B,
god.
you have to do the transform, to the
Yeah.
inverse transform.
No.
So you are given this now. It's from A, you get this. Study from the part A, you get this. Okay. Now, if you want to transform, you can break this to 2 into this format.
Partial.
It can be A, partial fraction expansion. So A is this, B is this. So you can write in this form.
Dah
Okay.
lupa rasa macam mana nak buat partial fraction ni.
Ha?
Lupa habis lah.
Lupa habis. Itu kena study.
Jenuh.
So from there, because I'm not going to cover all these math, that one I consider you already know. So,
Don't consider, don't.
so this function actually can be written as that. So from there, this part is actually this E minus AT UT, and this part is this E minus BT UT.
Dia transfer balik jadi ni lah, time domain
Yes.
lah. Oh.
Yeah. So basically, this is what we are doing is that we do the inverse Fourier transform. So this actually we use these properties, this formula. This formula. This from here transform to that. Part A actually from here transform to this. Part B is from here to that. Okay. So you get the answer for part B.
Yeah.
Yeah.
Alamak.
So this
Lagi.
ada lagi. Now we are still covering the properties of Fourier transform ni. Differentiation. If x of f is transformed into Fourier into frequency domain using Fourier transform, becomes x of f as capital. Then the differentiation of nth order of x of t will give you j2 pi f to the power of n x of f. Okay, so basically that you just transform the x of t into x of f and multiply by this factor.
Oh.
Okay, that is the differentiation. So basically, you don't have to do differentiation in the frequency domain. You just multiply by a factor to the power of n. So that is another beauty of Fourier transform.
Fuh. Sir.
Yes.
Can we take 5 for take 5 kejap?
Okay.
Pening
Berapa dah kan?
12.5 saya.
12.5. Oh, okay.
Ui.
Kita ada banyak mana lagi ya? Ya, ada. Tak ada lah.
Habis lah.
Ai.
Macam satu slide je.
Basically ada 3 slide lagi. 2 slide. Tak habis dulu ke?
Habis.
Okay. So basically that a differentiation in time domain is just a multiplication by a factor of j2 pi f in the frequency domain. Itu je. So it's simplified. So basically kalau dy. Huh? Kalau apa ni of t dt, maka this one is j 2 pi f.
F.
Apa ni saya punya ni.
Jadi apa tu, sir?
Tak tahulah.
Ayo.
Alah. Okey. Aduh, habis saya punya ni.
Aduh, macam
Alamak.
Dah hilang dah.
Dah hilang.
sir.
Okey. Nampak tak?
Tak nampak, sir.
Tak nampak? Kejap. Tiba-tiba je. Tertekan.
Potong lah. Orang kena semangat ni.
Okey. Ya.
Yang ujung-ujung, sir.
Tu.
Okey.
Talis.
Dia kembali lah.
Kembali pun dia dah save dalam saya punya slides. Semua tanda-tanda tu. Aduh. Tapi tak apa, saya boleh ambil yang dalam apa ni, yang dalam MS Teams sebab yang tu tak ada ni lah, tak ada tanda-tanda. Basically, 2 pi f of x of f. Kalau double derivative, so basically this actually
2 pi f squared.
Correct. Kalau triple derivative,
2 pi f cube.
itu je. So the integration, the differentiation in time domain will result with the multiplication by this factor only. Example, find Fourier transform for signal g of t equal to a triangle of t using first order differential property from differential of gt dt. So basically that we know that this is the differentiation, the graph, the differentiation of this is this, differentiation of this is that. So this part actually we differentiate is that, this part is that. Okay. So now we just want to prove whether this differentiation property is correct or not. So we need to do the differentiation.
Oh my god.
So given dgt, the differentiation of gt over t is equal to this. It basically is a rectangular of t plus 0.5 minus a times rectangular of t plus 0.5. So take the Fourier transform for the above equation using the differential equation. So basically that you get this. If you do the what do you call it, the direct calculation, or if you do the differentiation using the formula. So the Fourier transform of the differentiation of g of t dt is actually equal to the what call it Fourier transform of rectangular of t minus so j2 pi f of g of t is equal to this. We should get this. So g of f is, when you rearrange, you get this. Right? Pi.
Sir, sangkut. Sangkut.
Sangkut.
Oh my god. Okey dah, okey.
Okay.
Okay.
So basically that's first, because you are given this function a triangle t, and we need to find the differentiation for this. Okay. So this function is actually the differentiation of gt of t is given by this. From the graph, we can get this function. Okay. So if we take the differentiation directly of this, I mean the Fourier transform of this, you go through the process, you get this a sin square pi f. Okay. But also, what you can do is that by using the properties, the formula we can get. We can just what we can do is that we can just take the we can do the Fourier transform of this, okay, and multiply by j 2 pi f, okay, which here. Wait, g of f is this. This is g of f. See, and f of, you just multiply by that. 2 pi f. So this is the transform of g of f multiplied by the factor j 2 pi f. Give you this. Okay. Okay. That is the Fourier transform properties. We have covered all of them.
Yay!
Yeah. So basically all 7 properties. First one is the distribution. Right? So these properties that related to the LTIC system, linear, time invariant, and causal system. So linear, time
Invariant.
Time invariant. Actually, we have this time shift and causal system.
Convolution.
Okay? This is causal, bukan convergent. Causal. Okay, so that is what we have on Fourier transform. So tomorrow, tomorrow I will cover the Laplace transform.
Oh yes. Mantap.
Then after that, I'll give you the what do you call it? The tutorial. Right?
Oh my god, oh my god. Okay, boleh sir.
Okay. Main memang banyak tau.
Betul.
Okay. So okay, thank you. Any question?
No, sir.
No sir.
No question. So what time is it now? 12:39, 12:40.
12:39.
So you have class at 2.
2 o'clock.
Yeah.
Yes, sir. 2
So I give you time for you to rest your mind because the lecture is heavy. The material
Yes
is heavy.
sir. Yes.
Terlebih heavy, sir.
Itu pun kita buat, I buat very brief, very simple.
Oh, tu pun simple,
Kalau
sir. Yang tu dah simple lah, sir.
that is the simplest.
Aduh.
Tak boleh nak simplify lagi dah. Kalau simplify lagi, you tak belajar apa-apa. That is the simplest in terms of Fourier transform that we can give it to you.
Sir.
Sir.
Yes.
Upload solution tutorial tu sir.
Yes, I will upload.
Alright.
Okay.
Sabar, San. Sabar.
Kejap lagi saya upload lah. So
Okay,
if you don't have any question, so I will release you for you to go for lunch before you go for the next class at 2 o'clock. Okay?
Alright sir.
Yes.
Alright.
Thank you, sir.
Okay. Assalamualaikum.
Assalamualaikum. Thank you sir.
Alright.
You sir, stay safe.
So I'm going to stop the recording. Thank you.